Now we'll study the speed of mechanical waves. First of all, transverse waves, which are mostly studied in solids only, although liquid surface is also of concern. But there we see in the form of ripples, and there is quite another type of formula. It's rarely used. If the transverse waves are produced in solid, you see the velocity for transverse waves in solid is going to be root eta upon d. D stands for density of the medium, and eta is modulus of rigidity, which is possible in solids only. This is the velocity of transverse waves. All these three have been given for the velocity of longitudinal waves. Longitudinal waves in solid, it is going to be y upon d. Y is Young's modulus, d is density. In liquids, that's going to be b upon d, that's bulk modulus. But in gases, you see here it is very important to point out that these relations were introduced basically by Newton. Newton suggested that velocity of longitudinal wave, that is sound in any medium, is given by V equal to root E upon D. What is E? E is modulus of elasticity. He also introduced the choice that you are free to use any modulus of your choice you are interested in. When it comes to solid, you see, obviously we are going to use Young's modulus. When it comes to liquid, obviously we'll use bulk modulus for liquids. But in case of gases where the options are two, there are two choices. If you study the velocity of sound in gases, in that case, knowing according to Newton that here it should be the modulus of elasticity, but since the modulus of elasticity in gases are of two types, then we are at a stage where two ways are looking and we have to choose one. Then modulus of elasticity for gases, is of two types, isothermal and adiabatic. Isothermal modulus, if you use, it's going to be P only, that is atmospheric pressure. And if you use adiabatic modulus, it's going to be gamma P. That means first you decide what type of process it is going to be when sound travels along the gases. In the gases, then it's isothermal process or adiabatic. This is to be decided. So, according to Newton, here it was a mistake by Newton, or you could say he could not be successful in giving the correct formula for velocity of sound in gases, because he suggested that sound propagation in gases is isothermal. That's why he used this relation. That was not accurate. Results were found inaccurate. Then there happened to be a scientist, Laplace. He suggested that propagation of sound in gases is adiabatic process, and he used adiabatic modulus, that is equal to gamma times P. So he replaced this pressure by gamma P, and he got the exact accurate relation for velocity of sound in gases. That way, what actually happened, we got the accurate formula. So, are we in a position right now to say that Newton's formula for gases was wrong? No, no, not the least. Newton has basically said that we are going to use modulus of elasticity in numerator and density in the denominator. Still, we are using modulus of elasticity in the numerator and density in the denominator. The only thing is that in place of isothermal, we are using adiabatic modulus. So, I think I have explained. Now, velocity of sound, P upon D, could be replaced by gamma or T by M on the basis of kinetic theory. So, same formula for velocity of sound becomes root gamma RT by M, whereas you see for RMS velocity it is 3 RT by